In this video, we're going to talk about calculating transfer functions now that we've solved for the response. This is a little bit complicated, can be complicated, and so we need to step back for a minute. And I want to pull up the slides from the lecture on the equations of linear hydroelasticity, just to review what it is we need to do to get these transfer functions. If you're doing a rigid body analysis and you're just wanting the rigid body motion transfer functions, those are easy to get. It's when you're doing a hydroelastic analysis and you want stresses and moments and forces and so forth, then it becomes a little more complicated. So we need to be clear on the steps we're going to take and what we're going to do. So I want to skip down to slide 10 here. Now this is the equation of motion that we're solving, that we solved for in the last video, the file called Hydro. We calculated MF star. So the star, remember, means that it's the modal matrices, modal values. So MF star, that's the added mass matrix. We calculated the CF star, hydrodynamic damping matrix. KF star is the hydrostatic stiffness matrix, and these are all modal matrices. So in our particular case for this problem right now, they're all 18 by 18 matrices because we're dealing with 18 modes. And YQ is the generalized coordinates, and that's what's in that array that we talked about in the last video. F sub F star, by the way, are the wave excitation forces, the incident and diffraction forces. Okay, so we've got YQ, and these are the generalized coordinates. And so the YQ for each frequency, that's the transfer function for that modal coordinate. But how do we get the transfer functions for physical, quote-unquote, physical coordinates? For example, the displacements at a specific point, or the, say, the moment or the force at a specific point. So we want to go down to slide 13 here. If we look at this equation right here, this will give us the transfer functions for the nodal displacements. We need to set up this modal matrix, so-called modal matrix psi, and we've already got it for the nodal displacements, right? This is just the mode shapes, the displacements in each mode. So column 1 are the nodal displacements in mode 1. Column 2 are the modal displacements, the nodal displacements for mode 2. Column 3 are the nodal displacements in mode 3, and so forth. So when we multiply those by matrix by when we multiply y by psi, we get then the transfer function for each nodal displacement. So that's fairly easy to recapture because we've got psi already. Now, you're probably not going to want to calculate the transfer function for every displacement. I mean, the number of displacements, remember, can be quite large, in the thousands and thousands. So you're probably going to want to pick out certain displacements out of psi. In other words, you're going to pick out certain rows that correspond to the displacement that you want, and then use a subset of that big matrix psi to calculate the transfer functions for the displacements that you want. The approach to calculating the displacements for other quantities besides nodal displacements is similar. We have to define a modal matrix, and I just called it psi sub tau, just to kind of indicate that this is probably what we're going to be capturing, or stresses. And so what we need is we need to set up this modal matrix, and in each row corresponds to a specific response quantity. For example, the stress at a specific point, or the moment at a specific point. And then each entry, each column is the stress or the moment at that point for mode 1, for mode 2, for mode 3, for mode 4, and so forth. So we need to be able to do that. So we need to calculate those response quantities in each of the modes and then form this psi tau matrix. Then when we multiply by y, or multiply psi tau by times y, we'll get the transfer functions for the responses we want. And so that's what we need to do here. We need to set up the psi matrices because the multiplication is obviously trivial. All right, so let's look at the workflow document. And so we need to do, it's broken down into 2 steps here because of the somewhat complexity. The first step is we're going to define the modal matrix for the stresses that we want to recapture. And the second step is to then actually calculate the transfer functions for those. All right, and we're going to do both of those in this video here. So let's look at stresses.txt here. The first step is to read in the eigenvalue database. Setting up psi matrix doesn't have anything to do with the hydrodynamics, so we don't need any of those results. We just need to calculate the response quantities in each of the modes. So I'm setting up here, I've decided I'm going to find the stresses at 5 points. Now, in this file and in the paper where I presented these results, I decided to use the fiber stress, extreme fiber stress. So I need to calculate P over A. If you think of a beam, I need to calculate P over A, which is the average normal stress, and then my over I, or MC over I, moment times the distance to the extreme fiber divided by the area moment of inertia to get the extreme fiber stress. Honestly, if I had it to do over again, I would only do the P over A component. This model, because we've smeared the stiffnesses, the MC over I component really has questionable physical meaning. So, and the resolution of the model isn't like it's going to give you high accuracy in terms of localized stresses. So it's fine for nominal stresses, the P over A kind of thing, but it's questionable for the extreme fiber stresses. But because I did it in the paper, I'm doing it here, and it adds quite a bit of complexity. But in any event, so for our case, the P over A, remember N is the capital N is the plate variable, which is force per unit length. So what we need to do to get stress from that is just divide by the thickness. And that gives us the average cross-section stress on that cross-section. But in any event, so I'm using 5 points here. I've decided I'm going to do it at 5 points. And so I set up this matrix, which has 5 rows and number of modes columns, right? So I need to get these values for each of the columns, for each of the modes, rather. Similarly for the modes, same thing. All right, so now I need to go through each of the mode shapes and calculate the stress, these 5 stresses. Stresses, I'm using the term stress somewhat generically here to mean both N and M in this particular case. We're going to combine them later to get the actual stresses. So what I need to do is I need to copy the corresponding column from phi, that's the matrix with the mode shapes, into the matrix or vector dot disp. And then I need to be able to calculate the stresses from that for that particular mode shape. I need to do this one at a time because HydranXR calculates the responses for a single displaced shape, and so I need to do that as sequential. So I'm doing this loop over all the modes. So I copy the corresponding mode into dot disp. I need to define this matrix here, which is the local coordinates. It tells the element, the shell element, where to calculate the stresses, and so I'm having it calculate the stresses at the 3 for each triangle and the quadrilateral, I'm having it calculate the stresses at each of the vertex nodes. And then response is the command that has the program actually calculate the stresses for the given mode. And then I need to go through, those are stored in .min5s underscore RESP response. And this is similar for all the elements. So if you had different kinds of elements, for example, if you had beam elements, it would be similar. So I'm going through and I'm extracting the results for the points that I'm looking for. And so here I'm looking for the point at x equals 0, y equals 0, z equal to 1. So that's at the center of the top deck. And then I need to, because there are going to be multiple points, multiple values for that point, because we've got multiple elements contributing there, I'm going to take the average of those results. And then that gives me the values to put into my modal matrices. So then I do the same thing for coordinate 0, 0, minus 1. So that's the middle of the hull. And again, take the average. And then I do it at 0, 5, 0. So that's along the y-axis, at y equal to 5, it's 10 meters wide, right? So it's at the positive y edge of the box, again in the center, along the center line, or the center of the hull. And then 0, 0, minus 5, that's on the other side. And then I look at the response at minus 2701. So that's along the center line at the top deck and at x equal to minus 27 meters. So that's towards the bow, if you will, because the wave is coming, if we're looking at a 0-degree wave heading, that's coming from the minus x-axis, propagating in the positive x direction. So this is towards the front, the quote-unquote front of the barge. And then I come down here and I need to scale. So I'm scaling the N values, which are the normal forces, by 20. So remember, the thickness is 0.05, so I'm dividing by 0.05 or multiplying by 20. Similarly, the moments here, I am scaling them by the C over I value. And then I add them to get the stresses. And I write then the stresses into a file. And I print them to the output file here as well. But I write them to this binary file with this command, so I can read them later when I want to use them to calculate the transfer functions. So that's what we're doing. And so you can see that this is a little complicated. You need to make sure that the coordinates are right, that it makes sense to add. In this case, because the geometry is fairly simple, we can do some simple addition and so forth, and get the right values to combine to get the values we need. All right, so let's see. I think I'll just do this first. And let's see, this is stresses. And I'm going to resize this. I should just be able to do file in, and we get it. So you see it's gone through and it's processed each eigenvector. I'd set this print command here up so that I'd know which eigenvector it was being processed. And then this is the modal matrix here. There are 5 points, so it's 5 by 18. We have 18 modes. And so these are the values in each of the modes. Note that the values in the first 6 modes are very small because those are rigid body modes. And there are no stresses in those modes, right? So it's only then 1, 2, 3, 4, 5, 6, 7 here, this is the 7th column right here. That's the first vertical bending mode, and that's going to be then where we start getting meaningful stresses. All right, so I'm going to quit that and move on to the next step. So if I pull up the workflow document, the next step is to determine the RAOs using the file TF. So I want to open that file. Here we go. So I'm going to open that with BBEdit. All right, so a bunch of comments here to try to explain what's going on. So the first 6 components, and I refer to each quantity that we're calculating the transfer function to as a quote-unquote component. The first 6 components, I'm just getting the surge, sway, heave, roll, pitch, yaw response we would get if we were calculating this as a rigid body, essentially. Now, I'd like to point out that these are the results because of where I've defined the rigid body modes about, which is about the CG. These are the displacements, quote-unquote, of the CG. But we know the CG is inside that box. There's no point in, there's no physical quantity besides air inside that box. So it's not really the displacements of a specific point. And that's pretty typical of any of most floating structures. I mean, the CG is not going to necessarily correspond to a physical point on the structure. But nevertheless, I want to get at these values. So if you look at the paper, I compared these results with the results for rigid body. Now, these aren't going to be the exact same results as for a rigid body. Component 7, I'm getting the transfer function for mode 7, mode 8, vertical bending mode. So I calculate the transfer functions for each of the 18 modes, just in case I want them. Then these guys here, 19 through 22, I'm calculating the vertical displacements at specific points. And so I haven't formed that psi part yet, so I need to do that. I need to go in and I need to extract the nodal displacements in each mode out of the from the matrices to get those values. And that's actually through component 26, 19 through 26, because I'm getting the vertical displacements, some y displacements, and x rotations. And the stresses are these 5 guys here. We've already captured or got that psi matrix out, so we're good to go there. Now, we do need to read in the hydrodynamic database because that has the generalized coordinates. It also, because what we'd read in the eigen database in the hydro file, it also has all of the structural stuff as well. So it has everything we need. So now we need to form the modal matrix. So I'm defining pi. I want to convert the roll, pitch, yaw response to degrees. It's calculated in radians, of course, and so I want to convert those values that are calculated by the program into degrees. So I need this, so I'm setting up this conversion factor, right? 180 over pi to convert radians to degrees. And I'm putting that into this matrix temp 18. By the way, I'd set that up as an identity matrix here. That's going to recapture the transfer functions. That's going to be psi to get the transfer functions for the modal coordinates. And I don't want a 1 for corresponding to roll, pitch, yaw. I don't want a 1 on those diagonals. I want pi over 180. Or sorry, 180 over pi. So I put those in there, and then that's just removing some temporary values. So now I need to go in and I need to pick out the nodal displacements for the specific points that I want. And so you'll recall from above, I wanted some z displacements and y displacements and x rotations. And so I'm just going in and this corresponds to the nodal nodal ID of the displacement that I want. This copies the z displacements for node 28. And it does it for each of the modes, right? So then I come here and I put each of these T1s through T8s into the corresponding row to form the psi matrix. Now I need to read in the psi matrix for the stresses that I calculated in the stresses.txt file, and I'm going to join them vertically, these two matrices vertically. Actually, there's three matrices vertically. There's the temp 18, which has the rows corresponding to the generalized coordinates. There's the TMP, which has the rows corresponding to the specific displacements, and then there's the TMP1, which is the rows corresponding to the stresses. So I've joined them vertically into this matrix called hide mode mat. You can call this matrix, this final matrix, anything you want. The default is hide underscore mode mat, modal matrix. And then I just remove a bunch of stuff we don't need anymore. I print out that modal matrix just so we can see it. And then the command that then basically does the transfer function multiplication, the psi times a y, is hide tf. And I'm telling it here to list them per period, list them per period rather than frequency. And I want the RAO printed, just the RAO. So it's just the magnitude. Because remember, the transfer function's complex, and so the RAO says, okay, write the RAO, the magnitude to the .tf file. So hide underscore tf creates a .tf file with the transfer functions in there. All right, so we can go back to Hydran and run this file. This is going to be tf, and move this out of the way here. Let's move it down to here. File in. All right, it's done. So it's very fast, right? This is just a simple calculation, multiplication, basically. So this is the modal matrix. You'll notice that it's the first row is just 1, 0, 0, 0, 0, 0, because it's calculating the transfer function for surge, and similarly 1 for heave, 1 for surge, 1 for heave, and then that 180 over pi value for roll, pitch, and yaw, and then the remaining rows are for the other values. So this would be for mode 7, mode 8, and so forth. And so everything else in that row is 0 because it's just picking it out. All right, so let me load the database here. So you can see that it took a little bit of time. If we look at this, it's 59.8 megabytes. And so, like I said, the GUI is a little slower in dealing with larger files. All right, before we do anything else, let's look at the output file. I'm going to flush, it would help if I spell it right, flush the output buffer so everything gets written to the output file when I look at it here. Otherwise, you may not have everything in the output file. So this is just showing everything, and it doesn't really have any of the results. The results are actually written to a different file. So the transfer functions themselves show up in this .tf file, and I'm going to open that in BBEdit. So this is the RAOs only. Remember, we ask it to do the RAOs. It'll write out the complex transfer functions if you want, but we specified that -RAO option. So this is component one. Component one, remember, is search, and it gives us the transfer function as a function of period, and for each of the 4 wave angles that we considered, 0, 30, 45, 90. Component 1 is surge, and so at 90 degrees, which is beam C, surge should be basically 0, and it is very small. And if we come down to component 2, that is sway. In beam C's, sway should be very small, and we see that it is, and larger in beam C's. Similarly, in heave, there's going to be heave in any wave direction, so we see that there are values in each, reasonable values in each wave angle. And for one other check, one should kind of check, spot monitor, is that in large wave angles, large wave periods, long waves, the heave should approach 1, and we see that it does. So we get the RAO for each of the response quantities, and if we scroll down here, so the first 18, remember, are the RAOs for the modal coordinates. So that's 18, and then 19, if you'll recall, we start getting the RAOs for specific displacements, nodal displacements. So this is the z displacement of some node, I forget where. And then the last 5, and I'll just scroll down to the last one, which is 31. These are the stresses at the points we defined. All right, so you can use these values in this .tf file to plot or to however you want to manipulate the transfer functions. Let's come back to the application. So we can also plot the transfer functions, the RAOs, in the application. It's useful to maybe just do some quick checking of the transfer function. And I demonstrate that in the tutorials, the program tutorials on the website, but I just want to do it now just to demonstrate that one can do this. So what we want to plot is the RAO versus wave period. So if we look at what we have in the database, we have hide TF. So if I come up here and get the information on hide TF, by the way, I could do it this way too. Just type in the command directly and then select the array that I want the information on, select paste, and then come back to the application, and it does the same thing. But anyway, the point is here is that hide TF is a 3-dimensional array, complex because it's the transfer functions. And if we think of this 3-dimensional array as a box, and we take a slice of the box involving the rows and columns, then I refer to that as that slice as a table. So the first slice is table 1, and that corresponds to component 1, which would be surge. The second slice would be table 2, which would correspond to sway. Table 3 would correspond to heave, and so forth, And the last table, table 31, would be the stress at one of the points. I forget which one. So we can plot the RAO, which is a real value. So we need to take the absolute value of this to get the RAO. Maybe I'll put an S on there. RAOs, move the cursor there so you can see that. So I'm taking the absolute value of hide TF and I'm getting the RAOs from that. Now, we also want to plot it versus periods. So what we have here is we have the frequencies, but the wave frequencies, but I want to calculate the wave period. So I want to calculate, I need to set up a vector of wave periods, and that's just equal to 2 pi over omega, right? So I need to do that calculation. So I didn't do it in the text file, so I'm doing it here. I'm going to define 2 pi. First I define pi, and then I scale that result by 2 to give me 2 pi. And then I want to copy the frequencies to, what should I call it? I'll call it wave periods. Yeah. So I need to take the inverse of that. So power wave, so I'm going to raise it to the power of -1, and then I'm going to mistyped there, so you can use the up arrow to scroll back and then edit. There we go. Was unintentional typo, but it gave me an opportunity to demonstrate that feature. So power wave period, so we're at 1 over omega, and we need to scale that by 2 pi, right? Wave periods value equal to pi 2. Sure that's right. Looks right. Okay, so now we've got the wave periods in a vector, and we've got the RAOs in that three-dimensional array. So that's in the database of the program, the computational engine, but not of the GUI. So we need to reload the database. All right, so we can see, let's scroll down here, we have the wave periods here, and we have the RAOs here. Okay, so we want to plot the RAOs. So what are we going to, let's plot heave. We'll plot the heave RAO. In other words, this is the RAO for the generalized coordinate associated with rigid body heave. So if I come to here, I'm going to plot heave RAO, and this is going to be wave periods, seconds. This is going to be heave, and that's meters per meter. All right, so we want heave, so that corresponds to table 3. Notice we have 31 tables, so we need to pick which one we want to plot. And the wave periods are not in the same array, so I need to select the separate array that contains the wave periods, the x-axis. And we want to plot, there's 4 options here for y, and that's for the 4 different wave angles that we looked at. So let's plot them all. We'll plot that's 0 degrees, 30 degrees, I believe, 45 degrees, and 90 degrees. We're going to use symbols, although I don't think it's a wise idea, but we're going to do it anyway for right now. Because now the reason I don't think it's a wise idea is because there are so many wave frequencies that we're going to get kind of a little bit of a mess maybe, but actually it's not that bad. All right, so here we have the wave periods, the heave RAO for the 4 different wave angles. And we can see that they all go towards a value of 1 eventually, which they should for as the wave period gets longer and longer and longer. The beam C wave, there's the heave RAO and beam C's gets to 1 very much quicker because it's only 10 meters wide, and so you get to a wavelength that looks like a long wave much more quickly with a 10-meter wide structure than you do for, say, head C's, where it sees a 100-meter long structure. All right, so it looks good, and you can plot any quantity you want with this option here. Okay, so that finishes this video. We've covered how to calculate transfer functions. The transfer functions for stresses, forces and stresses takes some investigating into the command reference, looking at the different element help files and or help commands, and understanding what are the responses that are available to calculate. So with that, we'll terminate this video. And the next video, I believe, if we come to the workflow document, is how to estimate the wet natural periods and their natural frequencies and the wet modes, if you will.